I'm helping Minchen to present his work, and he cannot come to attend the conference due to visa issues. So nowadays, machine learning inference is increasingly deployed as online services, and these inference services usually need to handle highly dynamic and unpredictable request patterns. So for example, the figure here illustrates 2 days of invocation patterns from real-world inference services, highlighting the burst and irregular nature of incoming requests. Online services are also required to meet strict listening SLO, such as that ensuring 99% of the requests are served in under 200 milliseconds. So among the cloud offerings, Serverless is well fit to host the inference tasks. First, it promises high scalability and allows functions to be quickly provisioned on demand, enabling elastic resource management. It also adopts pay-per-use billing and achieves cost efficiency. And the mainstream cloud platforms, including AWS and Alibaba Cloud, have enabled serverless-based solutions for model inference. However, supporting GPUs in serverless platforms is still a challenge. Currently, most platforms adopt an early banding approach. When an inference function is started, it is assigned to a dedicated GPU and kept there for an extended period. This method brings several fundamental drawbacks. The first is idle cost. So even if no requests arrive, users are charged for the GPUs that remain reserved but idle. The second is memory efficiency. Many idle functions continue to occupy scarce GPU memory, leading to low overall utilization. And the third, a 2-week production traces from Alibaba Cloud reveals that most functions are infrequently used. About 85% receive fewer than 1 request per minute, yet still consume GPU capacity. And the third drawback is cold starts with high latency. So as a workaround, platforms may aggressively reclaim idle GPUs to reduce the costs, but this means frequently cold starts. Restarting inference functions can take tens of seconds, easily extending the latency SLOs and interrupting user experience. And given these limitations, we will ask, what should an ideal serverless GPU inference platform deliver? So first, pay-per-GPU use. So ideally, users should only pay for GPU resources when they are actively performing inference, which delivers significant cost savings for users. And second is GPU efficiency. The platform should support fine-grained, efficient GPU sharing among inference functions, which enhances resource efficiency for platforms. And third, latency SLO compliance. It must constantly deliver low latency inference to meet strict performance guarantees. And moreover, these benefits should also be achieved without requiring the platform to access and analyze users' private model details due to the confidential reasons. And to achieve these properties, our key insight is late banding. So instead of banding models to GPUs, we keep models in CPU memory when idle and only move them to a pool of GPUs on demand with efficient model swapping. And this saves the cost when models are idle, and it allows multiple inference functions to share a pool of GPUs efficiently. As host memory is significantly larger than GPU memory, we can increase the number of models each GPU hosts and also achieve load balancing across GPUs. And moreover, model swapping is faster than cold starts, making it possible to satisfy latent SLOs. This approach can be performed within a GPU pool and be transparent to users, and the users need not to provide detailed model structure and information. So while late banding is promising, realizing it poses 3 challenges. The first is efficient GPU polling and model swapping. GPU polling and model swapping introduces additional communication overhead, and we need to reduce the overhead to ensure low inference latency. And the second is GPU memory management. Models are swapped in and out frequently, requiring seamless, rapid GPU memory allocation and deallocation. Efficient GPU memory management is critical to avoid fragmentation and slowdowns. And third, SLO compliance. Based on the late binding mechanism, we need to achieve efficient GPU sharing while meeting performance requirements. Next, we'll discuss the design of Torpor. So let's first look at the overview of Torpor. So there are two main components: cluster managers that manages resources across the cluster, and the GPU worker that hosts and executes inference functions. The key design here is the node-level GPU pooling. So at each node, all available GPUs are grouped into a shared pool, which can be dynamically accessed by different inference functions running on the server, on the worker. So when requests arrive at the worker, the intra-node router coordinates with the controller of the GPU server to make swapping and scheduling decisions. And it then forwards the request to inference functions, which dynamically access their GPUs through seamless CUDA API redirection. And this approach is performed transparent to functions that allows fine-grained and request-level GPU sharing. We next introduce how Torpor addresses the challenges one by one. The first challenge is API redirection and model swapping, as they can incur high communication and synchronization overhead. For example, a single inference request may involve thousands of CUDA API calls, which takes over 100 milliseconds for API forwarding and synchronization. And the loading model from host to GPUs between GPUs can also incur significant overhead, which is proportional to the model size. So to improve the performance of API redirection, Torpor performs group-level and asynchronous approach. We observe that the intermediate APIs of an inference execution are executed asynchronously. Only the output of the model is returned back to the function. Therefore, instead of synchronously redirecting every API call, we group and send them asynchronously, waiting only for the final output. This approach reduces the overhead down to nearly zero with no impact on correctness. Torpor also employs model pipeline execution to further reduce the overhead of model swapping. As soon as a layer of the model is loaded onto the GPU, its execution can be begun immediately. There is no need to wait for the entire model to be transferred. This approach allows overlapping the transmission of model weights and the computation, which further reduces the communication overhead. Now let's turn to the next major challenge, GPU memory management. Recall that with late binding, inference models are consistently being moved in and out of GPUs. This requires not only seamless swapping, but also highly efficient memory allocation. Torpor addresses this with two mechanisms. First, we enable automatic memory tracking and address translation. When a model is swapped between GPUs, its actual memory addresses can be correctly mapped to ensure a smooth and transparent migration. And second, Torpor is a layer to centrally manage all GPU memory allocations. It allocates all available GPU memory at bootstrap and internally reduces memory fragmentation. Compared to using the default CUDA memory allocator, our approach reduces the allocation overhead from more than 100 milliseconds down to nearly zero, which is important to achieving latency SLOs. And let's move to the third design, SLO compliance and resource efficiency. Torpor's primary objective is to maximize the number of SLO compliant function invocations per GPU node, which in turn improves the overall resource efficiency across the cluster. The SLOs here can be defined as like 98% percentile latency should be less than 100 milliseconds. Torpor adopts two designs in its policies. First, concurrent model swapping can easily cause PCIe bandwidth and contention, so it is crucial to design an efficient scheduling policy to reduce the PCIe bandwidth contention and improve end-to-end performance, which we term interference-aware scheduling. Second, the policy should also be made SLO-aware, which carefully determine priorities across requests to maximize the number of SLO-compliant functions. Next, we briefly introduce the two policy designs in Torpor. First, in terms of scheduling and model swapping, Torpor strives to minimize PCIe bandwidth contention across requests by taking into account both the underlying GPU hardware topology and specific model characteristics. For instance, Torpor routes data over faster NVLink connections whenever possible, which reduce PCIe traffic. It also considers the bandwidth intensity of different models and carefully schedules the models with high bandwidth demands. Second, Torpor incorporates SLO-aware request prioritization. For each function, we quantify the likelihood of meeting its SLO if it is scheduled at a particular time. Requests with a higher chance to be being SLO compliant are prioritized in scheduling decisions, and these policies work together to ensure efficient execution of inference requests and improve SLO attainment. Next, let's look at some evaluation results for Torpor. So here is the environment setup. We evaluate Torpor on top of a cluster of 6 GPU workers. Each worker node in our cluster is equipped with NVIDIA V100 GPUs, each with 32 GB memory and 384 GB host memory. We evaluate Torpor across a range of popular models, including the ResNet, DenseNet families, Inception V3, Efficient Net, and BERT. Now let's discuss the key benefits of late banding in Torpor. So first, Torpor can dramatically improve GPU efficiency and the total system throughput, especially under workload patterns where the functions are invoked infrequently. So in this figure, we stress test the Torpor and the native, which is an early banding approach by varying the per function request rates. As the rate decreases, Torpor can host more functions than native due to the efficient model swapping, which ensures that the GPUs are kept busy and maintain high throughput. Note that even with frequent model swapping, the latency is still sustained within 50 milliseconds. Second, Torpor achieves cross-GPU load balancing and maintains consistently low latency under dynamic request patterns. We set the per function request rate to 200 requests per minute and measure the normalized GPU load and tail latency. The results show that Torpor is able to distribute work more evenly among GPUs. This improved load balancing mitigates request queuing, resulting in lower tail latencies compared to the native. Overall, these results demonstrate that Torpor's late banding approach not only sustains high resource utilization and throughput, but also delivers reliable low latency inference. We next show the end-to-end results for Torpor. We deploy Torpor in a cluster and compare it against several baselines using real-world traces. So native represents an early banding approach, and the others use GPU pooling but without Torpor's optimization policies. We note that for native, the cluster cannot support over 500 functions due to GPU memory limitations. Other solutions also fail to sustain high SLO compliance as the workload scales. Only Torpor can meet SLOs for all functions, even with over 100 concurrent invocations. Furthermore, Torpor has been successfully deployed in the Alibaba's production service platform. The platform serves more than 150 users and has over 350 GPUs, handling over 400,000 inference requests per day. So thanks to the late banding design, it reduced the user's cost by an average of 70% and saves approximately 65% in GPU resource consumption, delivering significant cost savings in production environments. So let's do a quick summary. Torpor is a practical, usable, and resource-efficient serverless inference system. The key idea is late banding and model swapping. It provides several benefits. First, it enables true pay-as-you-go billing for GPU resources, which delivers direct savings to users. Second, it supports dynamic model swapping and fine-grained resource sharing, which improves GPU utilization. Third, combined with efficient scheduling policies, Torpor can effectively improve inference performance, and satisfy latency SLOs. And importantly, all these benefits are achieved without requiring access to users' model details, preserving the model confidentially. And that's all for the talk. Yeah.